Okay, in this video I want to talk about calculating a double integral over polar coordinates. And you're mainly going to use double integrals, you're going to use polar coordinates oftentimes when you're integrating over a circular region. And here's the basic formula that converts back and forth. Remember, x is r cosine theta, y is r sine theta, and x squared plus y squared equals r squared. And d is the region that we're integrating over in the plane. So, for example, suppose our problem is to find the area under the plane 6x plus 4y plus z equals 12, and above this disk in the plane x squared plus y squared equals 2y. So the first thing I'm going to start off doing is just graphing this region, x squared plus y squared equals 2y. And the way that we do that, this is going to turn out to be circular, and you can see that by completing the square. So if I subtract 2y from both sides, remember the coefficient, if there was an x term we'd have to do this as well, but there's only a squared term. You take half the coefficient of the y term, which is, so 1/2 of negative 2 is going to give us negative 1. Then we square that and we put it back into the left-hand side. Well, since we add 1 to the left side, we would also have to add 1 to the right side. Okay, so I've got videos on completing the square if you need to see that part of it. And now we can write this as x minus 0 squared plus y minus 1 squared equals 1. And this is a circle. It's centered at 0, positive 1. So 0, 1 would be right there. And then it has a radius of 1. So our circle that we're integrating over in the plane would just be a circle of radius 1 that looks like that. Okay, in terms of our angles, this is going to correspond to theta equals 0 to theta equals pi. If we go from one end, we would have to go all the way around the circle to get to the other part. Also, we have that x squared plus y squared equals 2y. Well, remember, x squared plus y squared, that's equal to r squared. We know that y is equal to r sine theta. So if we divide both sides by r, we'll get that r is 2 sine theta. Okay, so in conclusion, it says that the region that we're actually integrating over, we're going to let theta be trapped between 0 and pi, and our radius value is going to be trapped between 2 sine theta, so 2 sine theta and 0. Okay, so now we just have to set up our integral and calculate this thing. Okay, so I'm definitely interested in these values because they're going to give me my limits of integration. So let's see what would happen. We can rewrite our function as z equals 12 minus 6x minus 4y. Okay, so we're going to be integrating from, okay, so our theta values are going to be from 0 to pi. We figured out that r was between 0 and 2 sine theta. The function that we're integrating over is 12 minus 6x, but x is r cosine theta, minus 4y, which is r sine theta. And then let me erase my little region here. Because remember, we also have to tack on from the formula this extra r dr d theta that's present in the formula. So don't forget about the extra r because it's easy to do so. Okay, so now we're basically just integrating all of this stuff. Okay, so probably the first thing I would do is distribute this out. So you would get from 0 to pi, and then if you distribute the r, so we'll still have from 0 to 2 sine theta, we'll have 12r minus 6r squared cosine theta minus 4r squared sine theta. And then again, we're going to be integrating this with respect to r and then with respect to theta, so dr d theta. Alright, I think I'm probably going to cut this video here, and I'm going to actually integrate it in another one because this is going to be kind of long and tedious, so I'm sure I'm going to step over the 10-minute time mark. So dig around. The actual conclusion where I'll integrate it and evaluate it will be in another video.